worries. I hope you get well soon.
Yeah, thanks. Yeah. So Andrew, like maybe please, yeah, let's share that.
So sorry, I need to ask, like, how do I correctly pronounce your name? It's
Yeah, no, it's Friederike.
Friederike. Okay.
Yeah,
All right.
but I'm flexible, so it's fine.
All right.
Don't worry.
All good. So yeah, probably let's wait for like a couple more minutes. Probably like like some people are still trying to join.
Yeah,
Um
sure.
and so you're currently in Aachen, if I'm is
Yes,
that
that's correct.
okay?
Yeah, I'm
Awesome.
doing my PhD there. So
I see. Nice. Um so who are you working with in Aachen?
I'm in the group of Professor Markus Müller.
Ah,
I don't know if you know him. Yeah.
mhm. Awesome. So yeah, okay. So probably you want to try and share your slides, see if it's working
Yeah,
well.
I'll try. I don't usually use Microsoft Teams, so
Yeah.
probably no. Is this working? Can you see the slides?
No, I see like this one line of like Sear Talon. Yeah, it says something, but not
Okay.
it's not the slide. So yeah, there should be a share button, like yeah, where yeah.
Now, can you
Yes,
see the
perfect.
slides now? Okay, that's
Yeah,
good. Yeah.
awesome.
Usually in Zoom, I just know that you have this green bar around it, then you know you're safe.
Yeah, no worries. Yeah, for some reason, like people in Singapore likes to use Microsoft Teams instead of Zoom, but yeah.
Yes, just varies.
Mhm.
But is it possible to see the call at the same time? So see if people ask questions?
Ah, yeah, like people have this issues before. I've never really okay, so I think if you click on your share button in Teams, like so it will give you like option of content only or stand out or like side by
I'll try
side.
again.
Yeah.
Um,
So I think like side by side option should allow you to see the to see us.
uh, sorry, I don't know. There's no other option, but I guess you can just notify me if there are any questions.
Yeah, okay. Yep, sounds good. So yeah, I guess or has the recording started yet? I'm not sure if sure is probably away. But okay. Yeah, anyway, let's just start. So yeah, so today we have Friederike from Aachen, and she's gonna talk about this measurement-free, scalable, and fault-tolerant universal quantum computing. So Friederike, yeah, take it away.
Yes. Yeah, continue sharing, sorry. Yeah, I'm Friederike Butt. I'm a PhD student in Markus Müller's group at RWTH Aachen. Yeah, and I'm very happy to be here and talk about measurement-free, scalable, and fault-tolerant universal quantum computing. Yeah, feel free to ask any questions in between, maybe just shout because I cannot see the video panels. So as we all know, the components in a quantum computer are noisy, which means that the information stored in physical qubits is easily corrupted. And so the idea is to encode information not in physical qubits, but in multiple qubits, such that if some component fails, we can still recover the initially encoded information. So which kind of operations do we then need to perform in these encoded states? So in general, we can take a universal gate set and approximate arbitrary computations with this discrete and finite gate set with in principle arbitrary precision. So for example, we can take the Hadamard gate, the CNOT gate, and the T gate, and with this then approximate computations efficiently. And how can we now implement this universal gate set on this encoded logical level? And for this, we can use these transversal circuit designs. Transversal meaning that essentially you use a bitwise gate implementation such that errors don't spread uncontrollably within one encoded block of qubits. So for example, in this circuit here on the right is a Hadamard gate on the smallest instance of the two-dimensional color code. And essentially, the number of errors before applying this gate is the same as the number of errors after applying this gate. So if we can now implement this universal gate set in a transversal manner, we would directly achieve fault-tolerant universal quantum computing. But this is not possible because there's this Easton and no-go theorem that states that no quantum error correcting code exists that has this universal transversal encoded gate set. So in other words, if we have some quantum error correction code A, and we have a transversal implementation of the logical Hadamard gate and the C0, we will miss a transversal logical T gate. And one can now use different methods to circumvent this. So for example, one can use magic state injection, which I will not talk about today, but a different method called code switching, where essentially we take a second code B with a complementary set of transversal and therefore natively fault-tolerant gates. And the idea is now to transfer encoded information between these two codes and in that way gain access to the full fault-tolerant universal logical gate set. So if we, for example, take some algorithm that we want to run on physical qubits that contains this full gate set, so Hadamard T's and C0s, we can now shift this to the logical level. But now each logical gate is only applied in the regime on the code with the respective transversal gate implementation. So for example, here on the bottom right, we want to apply the logical T gate in code B, but then in order to be able to apply a logical Hadamard gate, we first have to switch to code A to use the transversal gate implementation. So in the end, the goal would be to run a full quantum algorithm that includes this fault-tolerant universal gate set and potentially quantum error correction rounds in between these logical operations for fault tolerance. And here, one challenge is often that these logical operations require mid-circuit measurements and real-time feed-forward. And this is still experimentally highly demanding. So for example, in ion traps and neutral atom platforms, these measurements are slow, and especially mid-circuit measurements during a computation takes a lot of time. In addition, this real-time feedback, so when you want to measure a subset of qubits and then conditioned on this outcome, want to apply some operation or not, this has been realized experimentally, but still is very challenging and can induce very high error rates. So the question was, can we get rid of these mid-circuit measurements and in that way improve the performance of our logical algorithms? And this is essentially what I will talk about today. So how can we implement all of these logical operations without mid-circuit measurements or feed-forward operations? So I will start by very briefly talking about the codes that I'm considering, which are the 2- and 3-dimensional color codes, and then talk a little bit about fault-tolerant code switching, which we can then modify such that we don't require any measurements. So in the end, I will then talk about how to realize measurement-free fault-tolerant quantum computing and how to scale this up to high-distance codes. And again, feel free to interrupt at any time.
So Friederike, a simple question, very naive question. So I mean, I think you will not touch upon maybe this other approach, which is the magic state distillation. But just wondering, I mean, so there are these two approaches, prominent approaches. One is this state injection, and the other one is code switching. So I have two questions related to that. First is that in magic state distillation, I mean, I agree that the mid-circuit measurements, they are costly, and obviously one would want to not have. On top of that, the applying operations like unitaries in many platforms is easier. On the other hand, measurements take time. So you would want to have measurement-free scheme. But let's say I compare it against something like, I don't know, magic state distillation, or let's say the recent version of that, like something like magic state cultivation, which appeared recently, So compared to that, like, I mean, do you think like this is like a more promising approach, the code switching? Or let's say, I mean, in parallel, it's perfectly fine, even if it's not, I mean, we'll answer it. Even if it's not, maybe let's say code switching is something that you would like to explore. I would just want to ask, like what is the largest two codes, like largest codes with like a highest distance for which code switching protocol exists. I mean, I know only for few examples where people have talked about code switching, but in general, like, are you aware of, like two largest codes with, like distances, I don't know, like 30 or 40, such that, like, I mean, we can suppress error to like a good value, and at the same time achieve universality also by code switching.
Yeah, so this is basically a two-part question, as I understand. So first, the comparison to magic state injection or distillation. So there are some works that try to compare code switching and magic state distillation. However, the comparison is always difficult because those are two different ways to implement some logical operation. So in the end, you want to implement a logical operation, and magic state distillation is just a method to prepare certain resource states, which you then have to inject, which you don't need for code switching. So in code switching, you in principle don't need to prepare logical resource states, which in the end, as magic state distillation usually relies on some probabilistic preparation of these resource states, which you don't need. But we also compared the performance of these two approaches for magic state injection. So the overall error rate that you would get for applying a certain logical operation. And we find that, for certain noise models, so it strongly depends on which architecture you consider. So what are typical noise processes in your setup? And we found that these can actually perform comparably. But yeah, as I said, this strongly depends on the noise model that you're considering. And as you also mentioned, this trade-off of how many mid-circuit measurements do I have to perform? How well do my 2-qubit gates perform in comparison to these measurements? And as far as I know, there are not detailed studies about this out there yet. As for measurement-free magic state distillation, this doesn't exist yet. So I can't really compare to that. And then the second part of the question was, what's the highest distance code that I know that allows for code switching, if I understood correctly. And in principle, this is not limited by code distance. So you can take any two-dimensional triangular color code and then perform code switching with a respective 3D code version of the same distance, which might become clearer later on. But this is in principle not limited by code distance. Does that answer your questions?
I think first question you maybe answered, but second question, like, I mean, I was thinking like maybe, like a specific example. Like obviously, like, I mean, for code switching, you want to preserve information when you go from one code to another. And in the process, like apply let's say the transversal T-gate in the second place. But I was thinking, like, I mean, in the literature, like, I mean, all the examples, for example, that, I mean, I'm aware of, they are like 712 code versus 1022 code, 713 versus 1022, or things like, 2D color code and 3D color code, like which also like 7 qubit and 15 qubits and like, and this, I mean, obviously one can concatenate and through that some threshold can be obtained. But I was thinking something like, I don't know, distance 50 code or distance 20 code, like something similar to like the recent QLDPC codes that we have, like bivalent bicycle or something of that sort, like for which we know how to do code switching, like.
So in principle, the method is the same. Also, if you scale up to higher code distances, and you would just take larger codes, but the rest remains the same. I'm not aware of works who investigated this in detail. But I will also think about it and maybe come back to it later. Any more questions? Then I will continue. Yeah, so as we now already mentioned, so one can construct a two-dimensional triangular color code by placing qubits on the lattice of a three-valent, three-colorable lattice, as for example like this. And now these subsets of qubits form these plaquettes, which we label with colors red, blue, and green, like this. And we now define stabilizers on all of these plaquettes. So for example, this weight 6 Z stabilizer or this red X stabilizer. And in the following, I will only consider the smallest distance code instances, which we can then later on scale up to larger codes. But we choose this because this code is error correcting, so we can correct any single error, and also implementation of the logical Hadamard gate and the C0 gate, where we are lacking a transversal logical T gate. So how does this look in 3 dimensions? So if we now go to a tetrahedral code, the smallest code instance contains 15 physical qubits that encode 1 logical qubit, and again we have distance 3. So now we not only have these 2-dimensional units, but also these 3-dimensional units, which we call cells. And we now define the X-type stabilizers on these cells. So we have a red, blue, green, and yellow X-type stabilizer, each of weight 8. And the Z stabilizers are defined on the faces of the code. So we define 3 weight 4 Z stabilizers within this tetrahedron, then another 3 inside, and 4 on the boundary of this tetrahedral structure. And in this code, again, we have a set of transversal gates. So now we can implement a logical transversal T gate by applying single qubit T and T dagger gates. And this essentially works now because we have these weight 8 X-type cells, meaning that this overall phase that we get from these physical T gates cancels out, and we still preserve the stabilizer group. But now we are lacking a transversal logical Hadamard gate. So essentially we now have these 2 codes, so a 2-dimensional color code on the one side, a 3-dimensional one on the other side, and the 3D code has a transversal T gate, while the 2D code has a transversal Hadamard gate. So the idea is now to, for example, start in this 2D code, transfer the encoded information to the 3D one, apply the missing gate, and then switch back, and in that way get access to the full universal gate set. So how does this work? For example, if we switch from this tetrahedron to the Steen code in this direction. And now when I talk about the Steen code, this essentially corresponds to one outer face of this tetrahedral structure. So this red, blue, green triangle here on the right. However, in both regimes, all 15 qubits are always present. But on the right side here, this bulk, this yellow bulk, is present but doesn't encode any information. So on both sides, we now have these 2 stabilizer groups, so the tetrahedral and the Steen code stabilizer group. And essentially in the tetrahedral code, a code set is a +1 eigenstate of these weight 8 cells, while in the 2D code, a code set is a +1 eigenstate of these weight 4 faces. So what we have to do to switch from one to the other is first measure those stabilizers of the target code which are not initially fulfilled. So exactly these 3 X faces of the Steen code. And this would generalize to larger distance codes. So if you would have like a distance 5 tetrahedral code and a distance 5 2D color triangular color code, you would have to measure more X-type faces of this 2-dimensional color code, but the principle stays exactly the same. So this measurement is basically a random projection onto a + or -1 eigenstate of these X faces. So what one has to do in the next step is apply an operation that on the one hand doesn't change the logical state because we want to preserve the encoded information, but also fixes the state into the desired target code space. And we can do that by exactly applying so-called gauge operators, which in this case just correspond to Z stabilizers of this tetrahedral structure. So to make this more clear, one quick example. So we are looking at switching from the tetrahedron to the Steen code. And in the first step, we measure the 3 X plaquettes of the Steen code. And this is a random projection. So for example, we could get this measurement outcome 1, 0, 0. meaning that this red plaquette is violated. So in regular quantum error correction, we would just apply a correction to this top qubit here. But we can do this in this case because that changes the logical state. So what we do is we apply a phase type operation. So in this case, we would apply the interface between the blue and green cell, like this. So this overlaps at two sides with the blue and green plaquette. So we stay in a +1 eigenstate of these two plaquettes. And it overlaps only at a single side here with the red plaquette. So we fix the state also into a +1 eigenstate of the red plaquette. And this works completely analogously for the inverse direction. So to switch from the Steen code to this tetrahedral code, we would measure the Z-type phases that connect the Steen code with the bulk, and then apply a combination of these Steen X-type phases to fix the state into the desired target code space. So to summarize this part, we can switch between the 3D and the 2D code by first measuring stabilizers and then applying gauge operators, which just corresponds to phase type operations. But I have not talked about fault tolerance yet. So far, everything was perfect and there were no errors happening in our circuits.
Hey, Friederike. Sorry, so if I may ask something. So you mentioned that, okay, so after you switch from the tetrahedral code to the Steen code, then you get like this stabilizers of like this S stabilizer and S bulk.
Yes,
and you mentioned that S bulk does not encode any logical information. So I'm just thinking, if this is some kind of, I don't know, like a necessary condition for code switching, so whatever you have left to the qubits that are not in the new code that you're switching to, it cannot encode any logical qubits, or I don't know, like if there's something there, like regarding number of logical qubits.
Yeah. The overall idea is basically that these two codes correspond to two gauges of the same subsystem code. And in both cases, we want to encode one logical qubit, meaning that essentially 1 degree of freedom in this definition of our stabilizer groups is left, which means that basically in this regime of Steen and bulk, we want to encode this 1 degree of freedom, so our logical state, and we want to encode this on this Steen phase. And this bulk, in this case, this just contains 8 qubits and 8 stabilizers defined on this bulk. So this is just in one specific state, meaning that there's no degree of freedom left that could be encoded in this bulk.
Right.
But in principle,
Okay, sorry, go ahead.
Clarify?
Also I'm thinking like of something like, like a more general scenario, which Kishore probably mentioned a bit earlier, if your code encodes like just K logical qubits, and if there's like I don't know, like some kind of requirement that you want to move like all your logical qubits to your new code, and then whatever's left of like in this case, like you have like this S bulk, but in general you probably have like something analogous to that I don't know, like if like it's something like a general prescription not to left to move like all the logical qubits.
So this is given by your subsystem code essentially, and by the definition of your logical qubit. So let's say, the logical qubit, for example, here in this case of your tetrahedral code, you want to preserve that. So this is basically sort of fixed, and the remaining degrees of freedom in your subsystem code, I guess you can treat them as you want, but in the end, you cannot like increase or decrease the number of logical qubits that are defined in your system with code switching, because the logical operators also have to be equivalent in both regimes. So maybe to summarize, this is given by the definition of your subsystem code.
By the way, related to subsystem, like I have a kind of a tangential question, like maybe not directly related to talk, but about, so So like, do you have any intuition, Friederike, like that, like how many, like gauge qubits you normally require for that parent subsystem code to, like have the two codes allowing for code switching?
I'm not sure if this is defined by the number of gauge qubits that you have, or yeah, in some sense, I guess. So in the end, yeah, you define your subsystem code.
I'm asking because, recently we wrote a paper with Andrew and Derek in the audience, and like, we showed that there is a phenomena called contextuality that manifests if subsystem code has greater than equal to 2 gauge qubits. And we were thinking, like maybe it is related to some universality phenomena and all. And I was wondering if anybody has looked at, like showed that, code switching, the parent subsystem code must have at least 2 gauge qubits or something, at least.
I'm not aware of any work that does this. Okay, then I continue. Yes, I was talking about fault-tolerant code switching, and we'll just summarize this on a high level. So essentially, when you switch between two codes, you not only have to be aware of faults happening on auxiliary qubits during stabilizer measurements, but also of errors that happen on data qubits, because those will invert your random projection outcomes without you noticing, and can directly lead to a logical failure. So in the end, to make this fault tolerant, you have to measure stabilizers with some fault tolerant scheme, meaning that, for example, you could use these flag-based stabilizer readout schemes, but you also have to perform some additional stabilizer measurements to take care of these errors that can happen on data qubits. So in collaboration with the team in Innsbruck, we now implemented this on an iron-trap setup. And on these setups, what's challenging is that for these stabilizer measurements, you always now have to measure a subset of qubits, and then depending on the measurement outcome, apply some correction or operation or not. So we first looked at a smaller version of this 3D code that you already mentioned, the 1012 code. And essentially, if you look here on the right, fidelity drops if we add mid-circuit measurements. So really from this, the fidelity, the blue bar to the orange bar, this just means that one more mid-circuit measurement is performed. So this really affects the performance of logical protocols in practice. So yeah, what we then looked at is how to avoid this mid-circuit measurements altogether and to implement a measurement-free scheme for quantum computation. So I guess this would also be a good point for questions, because now I will not talk about code switching in detail anymore, but more about the measurement-free part. Okay, then I will continue with measurement-free quantum computing. The first fundamental question was, so there are these slow mid-circuit measurements and the need for real-time feedback. So can we avoid these operations in some algorithm? And first, in the last 2 years, there have been some works on fault-tolerant quantum error correction for small distance codes, so for distance 3 codes. And here the main idea is that given some logical input state psi, one prepares an auxiliary register in a suitable way, and then performs the error correction essentially as part of the algorithm itself in a coherent and autonomous way. And in the end, one has to discard this auxiliary register or reset it to remove the entropy from the system. But it was unclear, on the one hand, how to perform logical operations or a universal gate set, non-transversal operations in that sense, I should say, without measurements, or how to scale this up to high distance codes, because these schemes rely on multi-qubit controlled gates to implement some lookup table like decoder. And this is not directly or straightforwardly scalable to just larger code distances. And we could answer now both of these questions by building on code switching protocols. So the first idea is to implement measurement-free fault-tolerant code switching, and in that way gain access to a fault-tolerant measurement-free universal set of gates. And I'll now briefly outline on a high level how to do this, and then also show an explicit circuit before then scaling up to high distance codes. So this is now the circuit, and again we want to switch from this tetrahedral code to the Steen code. So in the first step, we prepare a logical auxiliary qubit in a suitable way, which in this case means that we pair a logical state of another Steen code qubit. So this is just a logical Steen code auxiliary qubit. We then map the information on the stabilizers that we previously measured. So basically the information about the 3 Steen X plaquettes from this data qubit register to this auxiliary qubit with just a transversal CNOT gate. Then we copy the syndrome information onto a subset of physical qubits. And then for fault tolerance, we also need to map out the bulk information. So essentially, the information about opposing stabilizers in this yellow bulk set are mapped to a second set of physical auxiliary qubits. So this is basically the step that we have to do to correct errors on data qubits that I mentioned before. And then we apply some Toffoli gate and basically update the previously extracted syndrome. And this basically fixes any falsely extracted syndrome bit if some error has already happened on a data qubit. And then we apply the first part of our coherent quantum feedback operation, F1. And then we need to reset our whole system. So this includes basically repeating all the previous steps, and then apply the second half of our coherent feedback operation, which is just a couple of CNOT gates. So maybe to be a little bit more explicit, this is now the full circuit here on the left that corresponds to this high-level scheme on the right for switching from this tetrahedron to the Steen code. So in the end, the information is then encoded on these 7 qubits of our data qubit register. The symbol here, with these double dots and 2 lines, basically inspired by musical notation, and that means that you go back to the beginning and repeat all the previous steps, meaning that you reinitialize your auxiliary register and repeat all these CNOT gates that you already performed. And essentially, to summarize this a bit, the first step is transferring the stabilizer information to your auxiliary qubits, and then perform coherent feedback within the quantum algorithm itself. And lastly, reset or substitute the auxiliary qubits to remove the entropy from the system. So these are always the 3 steps that are also used in these measurement-free quantum error correction schemes. But now, if you look here, we need Toffoli gates for fault tolerance. And so these are basically the only operations which are not essentially transversal CNOT gates. And we can use a similar approach for the inverse direction. So again, using logical auxiliary qubits and mapping in a stabilizer information from our data qubit register to these auxiliary qubits in a similar way. And in combination, this now gives access to the full measurement-free fault-tolerant universal gate set. As we can do the same thing as before. So for example, start in the Steen code, switch to the 3D code, apply the T-gate, and then go back. So what does this mean? So if we now look at some algorithm that we want to run, as for example, this one with Hadamard-Matisse, CNOTs, and quantum error correction, which operations can we now perform? Now we are considering as a base code a 2-dimensional color code. So basically every line here corresponds to this 7-qubit Steen code. And we can directly implement a set of operations in a measurement-free way. So the Hadamard gate is natively transversal, so we can immediately apply that by just applying 7 physical Hadamard gates. The same goes for the CNOT gate on a logical level. And we can now also implement the logical T-gate because we have this measurement-free code switching gadget now available. So we can also implement a measurement-free logical T-gate. Quantum error correction did exist before, so we can, in this case, directly integrate these measurement-free error correction schemes into this algorithm. So now we want to scale this up to high-distance codes. So we now replace, and we do this by concatenating the two-dimensional color code with itself. So we replace each physical qubit with another logical steam code qubit. And that means that the transversal operations generalize straightforwardly because every now logical Hadamard gate here on the right just corresponds to another weight 7 Hadamard operation in that sense. And the same goes again for the C0 gate. But as I mentioned before, this quantum error correction and the switch contained a Toffoli gate, which in this case is now a logical Toffoli gate. And if we look at this decomposition of the Toffoli gate, we immediately see that this again contains a full universal set of gates, so Hadamard T and C0. So what we have to do is we have to now include additional switching steps on the lower levels of concatenation to gain access now to this T-gate, essentially. And now by incorporating this logical Toffoli gadget, we have now access to all these components. So we can now again implement the logical T on any level, meaning essentially for any code distance, as well as quantum error correction, just by concatenating the 2D color code with itself. So we then ran simulations, first some Monte Carlo simulations of code switching of measurement-free code switching in both directions. First, for a very simple single parameter circuit level noise model. So every component in the circuit introduces some error with the same probability P. And this is what we find. So these are the logical error rates for different physical error rates. For fault-tolerant in red and green, and non-fault-tolerant code switching in both directions. And first we can essentially verify fault tolerance on the one hand because we find a quadratic scaling for the fault-tolerant protocols, but we also perform fault path counting to ensure that no single fault leads to a logical failure in the end. And we find pseudo thresholds at about 2 × 10⁻³ for one direction, and roughly 3 × 10⁻⁴ for switching from a Steen code to the tetrahedral code, which means that, so this is highly asymmetric, meaning that switching from the Steen code to this tetrahedral code is much harder because we have a larger gate overhead essentially than switching in the other direction. And that in turn means that these logical algorithms will be limited by this step. So this will dominate the logical error rates. We then also approximated the logical error rates with a leading order error polynomial, again by just performing fault path counting. So deterministically placing all way 2 faults in the circuit and counting how many configurations lead to a logical failure. And these are now these gray dashed lines that you can see here. And these essentially describe the logical error rates we get from Monte Carlo sampling reasonably well. So then the question is, why should I use measurement-free quantum computing? So is this actually advantageous? So we now compared a measurement-free and measurement-based protocol and try to investigate when is which protocol advantageous. So we introduce now a second parameter which corresponds to dephasing noise on idling qubits during measurements. So we have these 2 parameters, so gate error rates and errors during measurements. And essentially, we can now look at different parameter regimes. So we looked at error parameters of current trapped ion and neutral atom platforms that you can see here correspond to these shaded areas here and here. And in this plot, basically the green area means that the measurement-free protocol outperforms the measurement-based one, and most of these shaded areas lie within the green region, which means that in these setups, in a first approximation, these measurement-free schemes can be advantageous. However, of course, this depends on implementation details and the exact error model that you're considering. So it depends on shuttling schedules, for example, for trapped ion platforms, or how you bunch ions together for measurements, and so on. So this is just a first approximation, and just means that measurement-free quantum computing can give an advantage, but it will still depend on architecture-specific details and the protocols and algorithm that you actually want to run. So yeah, to maybe briefly wrap up, in our recent work, we now implemented a fault-tolerant universal gate set by constructing measurement-free code switching schemes. And then we could scale this up to, in principle, arbitrary code distances by concatenating the 2D color code with itself. And we find that these protocols are in principle suited for trapped ion and neutral atom platforms because they have all-to-all connectivity, but also have especially slow mid-circuit measurements and are prone to dephasing during measurements. But so far, we also assumed a rather conservative noise model, as, for example, we assumed that yeah, errors on single qubit gates are as large as errors on 2 qubit gates and so on, which is in practice, of course, not true. So ongoing work, on the one hand, will include further circuit simplifications. So we have some ideas of how to reduce these circuits and reduce the overhead, and then tailoring these protocols to specific noise models, as, for example, bias noise, which is present on trapped ion and neutral atom platforms. Yes, and this is all that I wanted to talk about, and I'm open to any questions that you might have.
All right. Yeah. Thanks, Friederike, for a very interesting presentation. And yeah, just if you like to ask any question, please just unmute yourself and ask away. Okay, probably since probably like people are still thinking of questions. So I have one question. So how does the number of auxiliary qubits does it increase with the size of your triangular color code?
Yes, if so, you can still see my slides, right? Because I shifted. So if you would increase basically the size of your code, so the code distance, also the number of auxiliary qubits would yeah, similarly increase, since you're looking at logical auxiliary qubits in this case. But the bigger overhead you would get if you would just increase the code distance, you would need like multi-qubit control gates to do this fault tolerance check, essentially. So you would not only need like controlled gates, but maybe 4-qubit controlled, 5-qubit controlled gates, depending on your distance. And this will give you the biggest overhead in qubits and gates. So this is why you wouldn't want to go for larger code distances, but use this concatenation scheme.
I see. So like the Steam code in particular, you use this Toffoli gate because it's okay, it has a distance 3. Okay.
Yeah. Yes.
I see.
And you will not need to go to higher, like 4 or 5-qubit control gates if you stick to this concatenation in principle.
Right. Interesting. Yeah. Does anybody else have any question?
Like Friederike, I have like a very say, okay. So there were like some work, right? I think by I don't know by Inca UAM, like they also did some, I think, but for permutation invariant code or something like like there was some measurement-free code switching protocol. So I was wondering if you have some thoughts, some intuition, like if you can make some comment. I don't.
Maybe I'm not aware of this work. So could you repeat? So you said
Yeah,
there was already work on.
Yeah, I mean, no, not already, maybe simultaneous or something, but what I could find a work on just for measurement-free code switching, but for I think permutation invariant codes, and maybe you guys like looked at other codes and all. But I think maybe it's not relevant because I think you haven't maybe didn't have chance to look at that.
I
have
sorry, I'm not aware. I don't know about these permutation invariant codes.
Sure, no
Sorry.
worries. Another question, like I have related to, so let's say, obviously, like, I mean, we have this Braviconig, like, which says that you need to go to higher dimension if you want to, like, have universality. And but then, like, there is no guarantee as such that, like, let's say if there is a code in 3D, it will definitely have transversal implementation of a T gate. I was wondering, like, I mean, are you aware of any sufficient condition or necessary condition, like which, let's say I give you a code and let's say it's a 3D code. I mean, whether it has transversal T-gate implementation or not.
Yeah, I guess the first thing one would check is how the stabilizers transform. So in the case of this tetrahedral code, this is straightforward because you immediately see you have these weight 8 X stabilizers. So these are preserved if you just apply single qubit T gates. So you don't get some weird phase from your stabilizers and you preserve your stabilizer group. I would say the same holds if you go to higher dimensions. You have to make sure that, this is preserved. So I guess you would need to go to higher stabilizer weights also.
Okay, yeah.
But this is more of an intuition, not like a thorough proof.
Would you know of any like nice examples of because like this one's like it looks very nice, like switching like this tetrahedral code to Steen code back and forth, and even if you scale it to like larger triangular color code, like do you know of any like a similar examples like in like just surface code?
Yeah, for example, I think what I've seen is basically a concatenated type surface code where you can then, so I think there's this equivalence between it's not a surface code in that sense, but a 2D color code. And when you turn off certain gauges, you will end up in a concatenated surface code. I can send you the reference in an email, maybe.
Yeah, I'll be interested to look into that.
There are some works on this, but I will have to dig it out.
Yeah, thank you. Yeah, so does anybody else have any question? Okay, going once, going twice. Okay, yeah, let's again thanks Friederike for the talk, and so probably Friederike, if you would like you could like share your slides and then like if people are interested, we could we will share them in the our Discord channel so people can go through them if you don't mind.
Sure.
Awesome.